Hi guys, it's Miss Rye again, and today we're going to be talking about the Heisenberg uncertainty principle. Our learning target is, I can use an inequality to describe the uncertainty principle. Now don't be intimidated because we're going to have several phases to this lesson. The initial phase is going to be the main assignment, and that's watching this video and completing the Google form that says Heisenberg's uncertainty principle main assignment. If you want to try some of the inequalities, I've included examples also in a Google form, but that is optional. So the main focus of today is learning the uncertainty principle, what it is, familiarizing yourself with the inequality, but you don't have to do the practice problems unless you want to. This can also be viewed as an extension from our lesson from last week, and you'll find out why here in a moment. So according to Chad Orzel from TED-Ed, the Heisenberg uncertainty principle states that you can never simultaneously know the exact position and the exact speed of an object. Why not? Because everything in the universe behaves like both a particle and a wave at the same time. So this is connected to wave-particle duality, which we talked about last week. Now we're going to watch the video, and then for your assignment, you'll complete the Google form. And it says 5/13/2020 Heisenberg Uncertainty Principle main assignment, not to be confused with the optional extension activity. Here we go.
At the young age of 26, a German physicist named Werner Karl Heisenberg published a landmark paper describing his theory of the uncertainty principle. Based on this work, in addition to the earlier theories that lay the groundwork of quantum mechanics, Heisenberg was awarded the Nobel Prize in Physics in 1932. To understand why this work was deserving of the Nobel Prize, let's dive in a little deeper. Quantum mechanics is the area of physics that examines physical behavior at the nanoscopic scale. There are 1 billion nanometers in a meter. Particles at this scale, like individual atoms and molecules, are so small that they are impossible to image. This is what makes the field of quantum mechanics so difficult and so crucial. Because we cannot directly observe physical behaviors at this scale, they are exceedingly difficult to understand and predict. The Heisenberg uncertainty principle relates to how well we can know the position and the momentum of a nanoscopic particle with certainty at the same time. Remember that momentum is the mass times the velocity of a particle. Heisenberg summarized his uncertainty principle as the more precisely the position is determined, the less precisely the momentum is known, and vice versa. What this means is that you cannot accurately know both the location and momentum of a nanoscopic particle. You may have heard the Heisenberg uncertainty principle in popular media described as an observer effect. This refers to the changes that a particle undergoes as the result of being observed, or put more simply, that the act of observing something changes it. The classic example is that if we try to measure an atom by using a super powerful gamma ray microscope, the gamma rays of the microscope would actually disrupt the tiny atom, making it impossible to image. But the Heisenberg uncertainty principle is more complicated than this. It derives from the fact that all matter behaves as a particle and a wave. While particles have fixed locations, waves are disturbances that travel through space accompanied by a transfer of energy and do not have a fixed location. Think of the waves that form when you drop a rock in a puddle. We can describe certain features of the wave, like wavelength, which is the distance between two successive wave peaks, but there is no actual location of the wave because it is always moving. Wavelength is directly correlated with momentum. An object with a large mass and a high velocity, like a moving car, has a huge momentum. Because the momentum is so large, the wavelength is very short. Thus, we can state that objects with high momentums have very small wavelengths. In the case of visible matter, the wavelength is always small, and that's why we can't observe the wave-like behavior. However, when we're dealing with very small nanoscopic particles, the mass and thus the momentum are exponentially smaller. This means that the wavelengths for nanoscopic particles can be larger. So in its wave state, we can determine the momentum of matter from its wavelength but not the position. But remember that matter behaves both like a wave and a particle. Particles, of course, have a known position, but they don't have a momentum because they do not have a wavelength. This is the root of the Heisenberg uncertainty principle. To know both the position and momentum of nanoscopic particles, we must observe both the particle and wave behavior of the matter. So how do we mathematically define this principle? According to the Heisenberg uncertainty principle, there is an inverse correlation between the accuracy with which we can measure momentum and position. In other words, as one measurement gets more accurate, the other measurement gets less accurate. In this equation, position is x and momentum is p. So delta x is the uncertainty in position and delta p is the uncertainty in momentum. You see that if you multiply delta x and delta p, they must be greater than h over 2 times pi. H in this equation is Planck's constant, which is the subject of an entirely different lesson. But we'll simplify it by saying that it's the constant that describes the relation between energy and wavelength and is a very small number. Since it's a constant, this means there's a value that we can look up and insert into the equation. The right side of this equation serves as a limit to how well we can know the position and momentum of the particle with certainty. If we increase the certainty of the position of a particle, the delta x goes down. As the delta x decreases, it begins to approach h over 2 times pi. The delta p will have to go up. This means that the uncertainty of momentum will increase and the uncertainty of position decreases. This is the root of Heisenberg's uncertainty principle. While we can observe both the position and momentum of something like a baseball, quantum particles are so small that we have difficulty measuring and understanding their behavior. The Heisenberg uncertainty principle relates to how well we can know the position and momentum of a nanoscopic particle with certainty at the same time. We learn that all matter exhibits behavior both like a particle and a wave. Particles have fixed, measurable locations, while waves have many locations that cannot be fixed, but measurable momentums. If we are trying to measure both position and momentum, we are measuring the two contradictory behaviors of the matter, which creates the uncertainty in measurement. We learned that the uncertainty between position and momentum is defined by the uncertainty equation. This equation provides the limit of how well we can simultaneously know the position and momentum of a particle with certainty as the Planck constant over 2 times pi. This provides a mathematical definition to describe the fact that the better we know the position of a nanoscopic particle, the less we know the momentum with certainty, and vice versa.
So we just went over the Heisenberg's uncertainty principle, and you saw the introduction to the Heisenberg equation. If that interests you, try the extension opportunities, but make sure you have a scientific calculator handy. You'll need it in order to do any sort of calculations with that formula. If you don't happen to have a scientific calculator, there are lots of apps that you can download on your smartphone. So that's it for this portion of the lesson. Now that you're finished, click over to the Google form, the one that says main assignment, and that's how we'll finish up. Thanks, guys. If you have any questions, be sure to email me at diana.rye@leepublicschools.org, and look forward to seeing you guys next week. Good luck.